Welcome back. So, this is lecture 8 in this course on mathematical tools. The topic of this lecture is exponential functions. So, in the previous two lectures, we talked about functions. What is a function? Function is a process that takes some input and gives you exactly a single value as output. Okay. And then we talked about inverse function, which is an inverse process for a particular function, right. So, let us say you have some function which takes the input x and gives you some output y. Now, inverse function of that particular function is an inverse process. It is a reverse process that takes y as input and gives you x as output, right. So, we talked about functions and their corresponding inverse functions, and we saw how to draw the graphs of functions and inverse functions and how to find domain and codomain of the functions, right. So, that sets up your foundation for talking about any complex function, right. But the kind of functions that we usually deal with in sciences are not just those linear and polynomial functions. We have much more complicated functions which involve logarithmics and exponential functions, right. So, in this lecture, I am going to introduce you to exponential functions. Right. You already know about exponents, right? We have covered that in, I think, first or second lecture. So, you would have a little idea about how exponent works, right? But there is a class of functions that you can build using exponents. So, let me show you how it works. So, suppose you have a function of this form, f of x equals to a to the power x, okay, where a is let us say any real number. A is a constant here, okay. A is a constant. What is the variable here? X is the variable. So, this is a function of single variable. A is some constant, x is some variable, okay. So, for example, a could be equal to 2. So, that means this function is, let us say, 2 to the power x. So, this is a function, okay, where you have the base is some constant and the exponent is a variable, okay. We call such functions exponential functions, okay, exponential functions. So, this is the generic form of an exponential function, f of x equals to a to the power x, where a is some constant. It would be a real number, okay. Now, depending on the base, this function would behave slightly differently. How? Let us give it a try. Let us see how the function behaves differently if the base changes, okay. So, let us take some examples. Let us say when a is equals to 1, what would happen if a is equals to 1? So, the function would be 1 to the power x, and what would be 1 to the power something? You are basically multiplying 1 x times, okay. If you multiply 1 x times, how much it would be? Well, it would remain 1, okay, does not matter, it would remain 1, okay. What if the power is, what if the base is a equals to 2, okay. If the base is 2, okay, what would be the function then? F of x would be 2 to the power x. Okay. So, what is the difference you see between this function and this function? In this function, the value of the function remains constant as the value of x changes. Okay. It would be a flat line parallel to x axis. In this case, the function is 2 to the power x. So, as the value of x changes, the value of the function would grow very rapidly. Let me show you how. So, let us say this is x and this is your function 2 to the power x. If you take, let us say x 0, then f of x would be 1. If you take x 1, f of x would be 2. If x is 2, f of x would be 4. If this is 3, then this would be 8. See, it increased from 1 to 2, 2 to 4, 4 to 8, right. So, this increment is growing bigger and bigger as you go, as you are increasing x by 1 unit. The y the outcome of the function is increasing. So, this is 4, this is 2, this is 1. Okay. So, this is multiplicative, right. This is not just linear additive. So, this growth of y is not linear. So, the y does not change by the same amount as x changes, y changes much more rapidly. Okay. We call this kind of growth exponential growth, right. We will see in the graph how it looks like. Okay. Let us take some more example. What if value of a is 1 by 2, okay, half. So, when value of a is 1 by 2, f of x would be 1 by 2 to the power x, or you can write it as 1 by 2 to the power x. Okay. So, how this would look like? Let us say f of x equals to 1 by 2 to the power x. Basically, you are dividing all these terms, basically you are taking reciprocal of all these terms, right. So, 1 by 1, 1, 1 by 2, 0.5, 1 by 4, 0.25, 1 by 8, 0.125, right. So, you are now rapidly decreasing. So, value of y, the outcome is rapidly decreasing, okay, when the base is less than 1. Okay. What if the base is, let us say, minus 1? Okay. What would happen now? Okay, let us remove this for now. Let us just deal with a equals to 1, a equals to 2, a equals to 1 by 2. Okay. So, let us draw the graphs of all these functions. Okay. So, what would be the graph of the function when the base is actually 1? Okay. How the graph would look like when the base is 1? Okay. So, when the base is 1 here, f of x, then the value of the function would be 1. So, let me write f of x here and x here, right. So, let us indicate this graph using red ink. So, when base is 1, a is 1, okay, the graph would look something like this, parallel to x axis like this. So, as the value of x changes, the graph would have only one value, 1. Okay, that is it. But when the base is 2, okay, then graph is rapidly increasing as the value of x changes, right. So, when x is 0, okay, the graph is increasing, right. So, at x equals to 0, the value of graph is 1. At x equals to 1, the value of graph is 2, like this. At 2, it is 4, so like this. So, this is how the graph behaves. Okay. What would happen for negative values of x? On this side, interesting, what would happen is that the graph will keep on having very low values of the function, but it would never have negative values. Okay. As you keep decreasing x, right, like this. So, this is how the graph of 2 to the power x looks like. Okay. This is graph of 1 to the power x, and how the graph of 1 by 2 to the power x would look like. Now, in this case, the value of y is increasing as x is increasing in the positive direction. So, here it is 1, but it is decreasing like this. But it would increase in this direction as you take negative values of x, okay, it would increase in this direction. Why? Can you tell me why? If you take negative values of x, let us say x is minus 2, then you have 1 by 2 to the power minus 2, it would go in the numerator. So, it would become 2 square, right. So, the opposite thing would happen. So, basically this will keep increasing as the value of x increases in the negative direction. This is how the graphs look like. Okay. So, what do we notice? That when the function has greater than one base. So, when a is greater than 1, then the graph increases. Okay. So, you get an increasing graph, it is an increasing function. What does that mean? As the value of x increases, the value of y increases, and the slope also keeps on increasing, slope of the graph keeps on increasing. And when a is less than 1, then you get a decreasing graph, right? You get a decreasing function. As the value of x increases, the value of y decreases, right? And when a is equals to 1, then you get a constant graph. So, value of y does not change even when the value of x changes, right? So, when a is greater than 1, you get an increasing function. When value of a is less than 1, you get a decreasing function, and a equals to 1, you get a constant function. Okay. So, this is how the exponential functions behave, right. Now, there is a particular function which is called a standard exponential function, such that the base has a value such that it holds very interesting properties. It is an increasing graph, right? The value of e, this base, is somewhere around 2.3 something. This is called Euler's number. Okay. So, this is standard exponential function looks like this, f of x equals to e to the power x. So, the base is e, which is somewhere around 2.3 or something, right? But why? Why do we need such arbitrary number? By the way, this is an irrational number. Why do we need such arbitrary irrational number as base? Why not 2 to the power x? Because this graph has very interesting properties. One, that the graph of e to the power x, this is how it would look like. Okay. It would cut the y axis, of course, at x equals to 0, at this point at 1, right, 0 1. Okay. But the interesting property is this, that it cuts the y axis at 45 degree. One, that is the first very interesting property. Another, that the rate of change of values of y with respect to x, that rate of change is also e to the power x. So, by the amount with which the value of function changes with respect to values of the x, with respect to values of the input. So, rate of change of y with respect to rate of change of x is also equal to e to the power x. When we do differentiation, we would write these rate of change in this form, or dy by dx, right. That is a better way. The dy by dx is also e to the power x. Basically, rate of change of y with respect to rate of change of x. Do you understand rate of change of y with respect to rate of change of x? It is basically slope, if you remember from straight lines, right. In straight lines, when one unit of x changes, some unit of y changes. When another unit of x changes, the exactly same unit of y changes. So, the rate of change of y with respect to x remains constant for a straight line. But this is not a straight line, this is a curve. So, what happens is this, that if you take this particular, let us say this is 1 unit of x, corresponding to this, how much change has happened in the value of y? Okay, so, from this point to this point, y has changed a bit, very slightly, only this much. If you take this particular unit of x here, now here y changes by slightly larger amount, this much. But if you take 1 unit of x here, let us say here, okay, here corresponding to this, the amount of change in y is this much more larger, right. Similarly, here we are taking 1 unit everywhere, but this change in y corresponding to that 1 unit of x keeps on increasing. Okay. So, in a way you can say that the slope of this curve at each point is increasing, the slope is increasing. Okay? In a straight line, slope remains constant, but in a curve, slope may keep on increasing or decreasing or may keep changing. Right? In this curve, in an exponential function with a base greater than 1, the slope always keeps on increasing. But what is that slope at each point? Okay? What is the, you can ask that because the slope is increasing, then it must be a function of x, right? So, it should be increasing at some particular rate. So, what is the rate with which slope is increasing, or in a way what is the rate or what is the function for the slope, right? So, slope is not constant, it is a function of x, right? So, for lower values of x, slope would be smaller, for larger values of x, the slope would be larger, right? So, what is that function? That function also remains e to the power x for this particular exponential function e to the power x. So, whenever you have a function e to the power x, the rate of change on values of the function with respect to x is also e to the power x, right. You will understand this point better when we start doing differentiation. Now, let us take some examples and try to draw the graphs, right. By the way, you may not be able to draw e to the power x graph by hand, but in your calculator you often have this function where you will see an e, basically exponent, and you can put in e to the power something and you will get some value, right. So, you can always use calculator to draw e to the power graphs, right. So, let us take some function. Let us say function is e to the power 2x plus 1. This is an exponential function. Okay. Let us draw the graph of this function and let us first find domain and codomain. Okay. What would be the domain of this function? The domain would be what possible values x can take? Well, x can take all real values, right. So, let us write x belongs to R. What would be codomain? Codomain of this function. Now, you tell me, can an exponential function take a negative value? We have drawn different graphs of exponential function, this one, these here, can they take ever negative value? No, they cannot even be equal to 0, they always have to be greater than 0. So, the codomain is such that this value always have to be greater than 0, right. More precisely, e to the power something will always be greater than 0, right. So, codomain, you can write f of x would be greater than 0, right. Now, you can draw the graph. So, at x equals to 0, the value of y is e, not 1, e here. When x is, let us say, minus 1, let us say x is not minus 1, let us say minus 1 by 2, then the value of y would be 1 somewhere here. And when x is minus 1, then the value of y would be 1 by e. Okay. So, around 0.5 basically here. Okay. So, the graph would look something like this. It would be an increasing graph. Okay. Look something like this. This is not linear, this is exponentially increasing, we call it exponentially increasing. This is graph of e to the power 2x plus 1. By the way, there was one thing that we briefly touched, but we did not talk about, was that what values in an exponential function, what values the base can take. Okay. Now, we saw different behavior of the graph with base a equals to 1, a equals to 2, a equals to 1 by 2. Basically, when the value of a is 1 versus when the value of a is less than 1 and value of a is greater than 1. What if the value of a is less than 0 or 0? Well, the graph is not defined at a equals to 0, and when a is less than 0, then also we do not call it an exponential function, because the behavior of that function would change drastically if you take a less than 0, and it won't be defined at multiple points, right? Then it's not an exponential function. So for an exponential function, this is the condition for any exponential function, that the value of a, okay, that the value of a should be greater than 0 and x could be any real number. Okay. This is how an exponential function behaves. Okay. All right, let us take one more example. What if e to the power you have minus x plus 1? Okay. Now e to the power is negative. Okay. So let us see what would happen now. Of course, x can take all real values and the function has to be always positive. So you know the domain and codomain. Well, let us just see the behavior of the function. So when x is 0, the value of function is 1. But when x is, let's say, let's increase x in positive direction first. When x is 1, the value of function is minus 1 plus 1, 0. Sorry. When x was 0, the value of function is e. But when x is 1, then the value of function is 1. When x is 2, then the value of function is 1 by e. Basically, this is decreasing. So as the value of x is increasing in the positive direction, the value of function is decreasing from e to 1 to 1 by e. If you take 3, then it will become 1 by e square. So it is decreasing. If you go into negative direction, let's say minus 1, then value of e would be e square minus 2 e cube minus 3 e4, right? Now the value of e is increasing. Okay, the value of the function is increasing. So how the graph would look like? If this is y-axis, this is x-axis. So corresponding to 0, f of x is e. Corresponding to 1, f of x is 1, right? Corresponding to 2, f of x is 1 by e, so on. Okay, so this is how it goes on x on this side, and on this side this will keep increasing. Let's say this is e square, this is e to the power 3, e to the power 4, and so on, right? So if you join these dots, this is what you will observe. Okay, so this is the function, this is the graph of the function e to the power minus x plus 1. So what does it show? That if the exponent is negative, okay, if in the exponent you have negative x minus x term, then the function will decrease. Okay, so function would exponentially decrease, right? Okay, so we can take some more examples, but before that I want to tell you why this is standard exponential function. So actually this is a very important function for natural sciences and as well as for cognitive sciences. We use this function all the time to model several natural phenomena. For example, to model the population growth. Okay, so let's say the number of deers in a forest is this much. How much would be the number of deers in the forest after, let's say, 5-10 years, right? So to model that number, to model such population growth, we use exponential function because populations grow exponentially. Similarly, we use it to model radioactive decay. So with what rate the material decays with time, right? So for that we use negative exponential function. Similarly, we use it to model activations in the brain, right? So let's say with what rate activation increases, activation grows, and activation decays. So activation decay function could also be exponential, as well as how much amount of activation is received by, let's say, a memory trace or a particular network, okay, that could also be an exponential function. Okay. So, exponential functions are really critical for modeling several natural phenomena, including the examples I have given you. It's also important for example, for Boltzmann machines, right? And also its inverse function, which we'll talk about in the next lecture, the logarithmic function, is also equally important. We use logarithmic function all the time to model natural phenomena. Okay. So, it's very important to understand exponential functions and logarithmic functions, because you will be seeing them all the time in different computational models within cognitive science, in models of perception as well as models of decision making, in models of language processing. You will always find these exponential and logarithmic functions, and also in all neuroscience, right? These are everywhere. So, it's important to understand the properties of these functions. You should be able to draw graphs of this function. You should understand their domain and codomain, right? And later on, when we start doing differentiation, you should be able to differentiate and integrate these functions, right? So, in first half of the course, we will be dealing a lot with these exponential and logarithmic functions. All right, I will stop here. We can take some more examples in the next lecture when we start logarithmic functions, which is an inverse function of exponential functions, right? But for this lecture, I will stop here. I will suggest that you practice exponential functions from in-class exercises I provided in the lecture notes. Okay, and also work with some non-standard exponential functions with some different base. Let's say a is 1 by 3, then how the function behaves, right? So, you practice with all that. There is one interesting thing I can show you. What if the base is 1 by 3, okay, and the variable is x. So, the function is 1 by 3 to the power x. And you know, we draw the graph of such functions when a is less than 1, then the graph is decreasing. Versus, what if the base is 3 and the power is minus x? Okay. What is the difference between these two functions? Can you tell me? We discussed the proper identities, rules of exponents, right? This is directly, the question is from there. Okay. What is the difference between 1 by 3 to the power x versus 3 to the power minus x? They are exactly same, because 3 to the power minus x means that it is 1 by 3 to the power x. This is how you can write it. So, for this is true for any exponent. A to the power minus x equals to 1 by a to the power x. This is what it means. Okay. So, these two functions are same, and that is why you see, when you take negative power, it is a decreasing function, versus when you take positive power, it is an increasing function. Because when you take negative power, what it means is that you are actually doing this. This function can be written as e to the power minus x into e to the power 1, this particular function. This is e to the power minus x into e to the power 1. This is also one of the rules of exponent. I have broken this term in this way. Okay, 1 e to the power minus x is actually 1 by e to the power x, and this is e to the power 1. Okay, so this is what we have been plotting in this function. Okay. All right, so I will stop here and see you in the next lecture where we discuss logarithmic functions. Thank you.